Welcome to the project video for Milestone 1 that goes with the first class of this milestone. This module has a team video activity, so you should watch this video with your team or at the same time as your team. There are places in the video where you need to pause the video and work together. Take a moment now to coordinate with your team if you have not already done so. We are beginning the project for Engineering 132. In Milestone 0, you read about the memo from your client, Avery Lyon, of natural catalysts. As you saw in M0, your team will develop a MATLAB-based analysis algorithm to perform parameter identification on an enzyme reaction for a detergent formulation. We will be using data from laboratory experiments that look at how enzymes react with substrates to create a product over time. That process is modeled by a known equation, but we don't know the parameters for that particular detergent formulation. Parameter identification, therefore, involves identifying important modeling information from experimental data. In order to understand a little bit more about the context of our project, this video shows how enzymes break down different molecules in stains. Let's take a look. You can watch with me, or you can watch directly on YouTube by using the short URL you see here.
Most food stains are made up of a variety of different substances. These complex stains need a multi-enzyme detergent to fully degrade the stain. Each of these test tubes has exactly the same contents and illustrates the components of a complex food stain. We've marked the stain components with different colors and covered them in a colorless starch gel. Each enzyme will specifically target a different component of the stain. Now we add the detergent and enzymes. We are stirring the test tubes to simulate the mechanical action used to wash clothes. The enzymes start doing their job immediately. But the first test tube can't turn since there are no enzymes to help the detergent cut up the starch that surrounds the stain. The amylase in tube number 2, however, quickly breaks down the starch. Unless the detergent has more than just amylase in it, though, like the third test tube does, it can't cut up the rest of the stain. Here, the amylase cuts through the starch, giving the mayonnaise access to the mannan part of the stain. Meanwhile, the enzymes in test tube number 4 are quickly helping each other work through the stain. Just the pectin remains here, since there's no pectinase in the detergent. Only the last test tube has enough combined enzymatic power to fully degrade the complex stain. Here's how this translates into wash performance. Only a multi-enzyme detergent can completely and efficiently remove complex stains.
So in this video, we saw how enzymes work on stains and detergents. Now let's take a more general look at enzymes. In this project, your team will be considering how enzymes react with the substrate. A substrate is the material upon which an enzyme acts. In the video we just watched, the substrates were the stains. Enzymes are proteins that bind with a substrate and use their particular geometry to break apart that substrate into products. In the image here, we see that a substrate and enzyme come in contact with each other. Then the enzyme breaks up the substrate into the products. Like a lock and key mechanism, each enzyme matches the particular substrate in which it's turning into products. In detergents, the larger molecules that get broken down, that is the substrates, are things like starches, using the enzyme amylase to break it down, or pectin, using the enzyme pectinase to break it down. Breaking up these molecules can help the detergent wash out stains from clothing. The project that we are starting involves first-order systems. We will be using a first-order system model and finding the missing parameters for the model. These systems are called first order because their governing equation is a first order differential equation. Generally, the first order systems are time histories, meaning time is on the x-axis, and have the shape of this graph. This could also be reversed where the output reduces rather than increases. In this graph, you can see that initially there is a rapid increase in the output, and then, as time goes on, the output arrives at a steady state. This slide contains other examples of first-order systems that are common in engineering. Take a look at the different examples. There are many instances of first-order systems across the disciplines, and it takes just a few minutes of Googling to find lots of other potential applications of first-order systems. You will learn more about first-order systems and their derivations in your mathematics and engineering major courses. But for now, knowing that first-order systems are important is enough. Going back to our context of enzymes in detergents, there is a process of collecting data to understand the performance of an enzyme. This data collection happens in a laboratory and is used to figure out the rate of conversion, or the velocity, at each substrate concentration. Let's take a look at the figure from the project background a little more closely. First, look at figure 2a. Here the enzyme is mixed with a known substrate concentration S. Using real-time data collection or sampling, the concentration of the product is monitored. Early on, the amount of product being produced is at a faster rate. However, once all of the available enzyme sites are saturated with substrate, the product conversion slows down. You can see that over time, the concentration of the product goes to steady state. Figure 2b shows the same graph, with the tangent of the curve at the start superimposed on the graph. The slope of this line represents the rate of the product conversion due to the reaction with the enzyme. This is the initial velocity, or V0, for that particular substrate concentration. This data collection happens at a number of different substrate concentrations to determine how the enzyme rate of conversion, or velocity, varies as a function of how much substrate exists. Figure 2c shows the V0s from many substrate concentrations, all plotted on the same curve. This curve is also important, so let's take a look at it more closely. When a plot is made of the reaction velocities as a function of substrate concentrations S, this plot follows the Michaelis-Menten model, given by the equation V equals Vmax times S over Km plus S. In this plot, we know the model but not the constants Vmax and Km. These are the parameters. Vmax tells us the maximum velocity of the enzyme reaction. Km is the Michaelis constant, which is related to the affinity of the enzyme for the substrate. This value tells how well an enzyme binds with its substrate. A lower Km is a better functioning enzyme. So the Michaelis-Menten equation, again, is V equals Vmax S divided by Km plus S. The V is the velocity of the enzyme catalyzed reaction with units of concentration over time. The S in brackets is the concentration of the substrate, with units of the amount of substance per volume. Vmax is the maximum velocity of the reaction, with units of concentration over time. And Km is the Michaelis constant, which is related to the affinity of the enzyme for the substrate. It has the same units as the concentration of substrate. As an important note, Km corresponds to the substrate concentration when the reaction velocity is half of the maximum reaction velocity, Vmax. We care about all of this because the two parameters we need tell us things about the performance of the detergent, particularly that enzymes with a high Vmax catalyze reactions faster, and a high Km indicates that the affinity of the enzyme for the substrate, or how well it binds, is low, which translates into a poorly catalyzed reaction. On the other hand, enzymes with low Km have high affinity for the substrate, which translates into quick binding and a more effective reaction. So we have been talking a lot about chemistry. However, you don't need to know the chemistry to work on this project. This is actually a data modeling project where the Michaelis-Menten equation is needed. So just a basic understanding of what we've talked about so far is needed so that you can use the context to analyze the data and make decisions. There are three main project deliverables. First, your team will construct an algorithm and implement it in MATLAB to analyze the kinetic enzyme test data we will provide to you. and then create a detailed description of your analysis of the data set provided, including clear and easy to understand graphics that summarize the data. Second, your team will provide an error analysis that characterizes the accuracy of your approach to determining the performance characteristics of the system. And finally, your team will make a recommendation about what natural catalysts incorporated can honestly and ethically claim to its customers about the performance of the new enzymes. Okay, so we know that one of the major project deliverables is to construct an algorithm in MATLAB that uses the Michaelis-Menten model, which means we need to identify the parameters of that model, which are Vmax and Km. Parameter identification is about determining model parameters from available data. This milestone requires you to think carefully about different potential parameter identification approaches, the process of using or coding these approaches, and the consequences of those choices. Okay, now we're going to do an activity together in your teams. We're going to work on finding parameter estimates by using visual information only. So first we need to find all of the information for the activity. Go to Brightspace for your section, then navigate to Content, then Project, then Milestone 1. Pause this video to download the M1A video activity. You should find the link right under the video you are watching. Share the document with your team in such a way that all team members can simultaneously work on it. Restart the video when you have completed this and are ready to continue. You will get more instructions on the activity as we progress through the video. Okay, welcome back. We are going to start by finding the parameter estimates visually, which means looking at and using the information from the graph. The graph shown here is figure 1 in your activity and has clean enzyme reaction data. That is, the data have no noise. The real data from the laboratory will have noise, which means the data won't perfectly match a curve in the way the curve is displayed here. This graph is a time history of the product concentration, which is noted by the capital P in brackets. So on the x-axis is time in seconds, and on the y-axis is the product concentration as the enzyme reacts with the substrate. This graph shows two different substrate concentrations for the same enzyme, where substrate concentration 1, marked as S1 in brackets, is in blue, and substrate concentration 2, marked as S2 in brackets, is in red. The initial velocity, V0 sub I, of the reaction for each substrate concentration is determined by the slope of the curve at the beginning of the reaction. The value of V0 needs to be estimated for each of the substrate concentrations available, and the process would have to be repeated for each enzyme under analysis. So what are the values of V0 sub 1 and V0 sub 2? In your teams, use the information from the graph in figure 1 of your activity to find actual numerical values for V0 sub 1 and V0 sub 2. And then describe your process to find these values. This should be done like you would with only paper and pencil. For now, do not worry about the fact that we will need to code this in the future. Pause the video here while your team completes part 1 of the class activity together. Then return for instructions for part 2. The obtained estimates of the initial velocities for all the substrate concentrations available are next used to create a plot of reaction velocities, V, as a function of the substrate concentration, S, as shown in figure 2 in the activity and shown here on this slide. From this new graph, you will estimate two additional parameters, Vmax and Km, considering the characteristics provided in your problem description. So, what are the values of Vmax and Km? In your team, use the graph in figure 2 of your activity to find actual numerical values for Vmax and Km, and then describe your process to find these values. Again, this should be done like you would with only paper and pencil. Don't worry about the fact that eventually we will need to code this process. Pause the video here while your team completes part 2 of the activity together. Return to the video when you are finished. Now that you have finished your video class activity, find the instructions at the end of M1A video activity sheet. Follow the instructions on this document for turning it in. Finally, Make sure all teammates have access to the final document of the M1A video activity that you turned in here for future reference. Now it's time to get started on Milestone 1. Download the Milestone 1 documents. For the first class of this milestone, focus on Part 1 and Part 2A. Part 1 has your team combining all of your individual problem statements into a team problem statement. Part 2A has your team brainstorming how to identify the parameters using a coding approach. Focus on what you did with the visual approach and think about how that might be translated into something automated using code. Don't start Part 2B. We will introduce the messy, noisy data seen in Part 2B in the next project video. Make sure to work on this part of the milestone before next class, because you need to be prepared to move forward in the next class. Make sure to ask your professor or GTA if you have questions about any of the content of this video.